Hello, everyone. So, good morning, good afternoon, everyone. It depends a bit where you are. We have people here from all over the world, so different time zones, and people are still joining. So, our experience with webinars is that actually most of the people are a bit late. So, we expect a bit more people coming, but we can start. We have reached the starting time. First of all, thanks for joining. We are extremely glad actually to see so many people joining in this webinar. It is quite a special webinar. We have never presented the stuff here before. We will be focusing on practice rather than theory, but of course there is a lot of theoretical background, and we really hope it's extremely valuable for you, and we can get a lot of feedback, and you will also learn quite some new things. So the topic of today is ozonation. It is a very interesting topic. I should not say this because most of you are ozonation professionals. So we are all fan of the technology. And we all know that it has some challenges. It has a lot of benefits. And we actually want to use the benefits, and we want to overcome the challenges. And this is why we actually produced kind of a novel engineering tool. It's quite a sophisticated simulation tool that allows to do this. So this is the topic of today. So we better get started because we have a lot of content to present. What are the objectives today? Well, first I will give a bit of a context. Why do we organize this webinar? So us, AM team, we have developed a novel simulation model for ozonation for engineering purposes. It is already available today through services, and the simulation tool itself will also become available very soon. So that's really the context here. And the fact that you are here means that you are kind of interested in learning more about engineering, but also general, of course, the process understanding. What are the objectives here today? Well, they are especially focused on you. So to provide you with some new detailed process insights, also to learn the basics of ozonation process simulation, because our assumption is that most of you are not familiar with this and really not really familiar also with process simulation in general. So some basic understanding is really important. But the most important objective is that you understand the practical application and the potential for process simulation for optimization, design, and the scale up of systems. So these are really key objectives. What is the format? It will be quite an interactive webinar. I warn you, there will be a lot of content, so it's quite heavy. It will be a full hour. We will try to focus everything or to put everything in 1 hour, but for the people that are still in favor of getting some more, we will also extend this webinar a bit, like 20 minutes or so for extra questions and answers, okay? But it will be a mixture between slides and live demos. So we will not be like for 1 hour presenting all the time because that would be a bit heavy. We will also invite you to answer questions. If you go over your screen, you will see a Q&A function. That's the Q&A tab, questions and answers. And my colleagues, I will introduce them later. They will be continuously monitoring this thread. And you can actually ask questions anonymously. We will also, if we answer questions live, not mention the name of the people who asked the question, but if they are interesting, we will answer them live. So please do not use the chat. You also have a chat window. Please use the Q&A. So then, we will also end the webinar with a short questionnaire. So let's start with some personal introduction and then some ozonation simulation basics. That's quite important. We will not spend too long there, but it's quite important. But then we go to the virtual experimenting and the virtual piloting, which my colleague Giacomo Bellandi will be doing. So we will go from batch to full scale. We will be looking at drinking water ozonation, wastewater ozonation, and I mean specifically wastewater effluent ozonation. So we will try to cover all these broad aspects. So personal introduction, who are we? Not too long because we will try to focus it on the ozonation stuff. But our company AM team, the name itself was derived from the A team. So the A team is a special force team. And we also kind of want to offer quite special modeling forces. specifically to the water industry. So we only focus on process simulation, and we help using very realistic computer simulations, technologists to optimize, to design, and to scale up their systems much faster and much more effectively. And we have customers all over the world. These are a couple of the logos here, some of our customers, but they are actually three categories. They are technology vendors interested in improving their technologies. We have end users or utilities interested in designing or optimizing their systems. And then we have consulting and engineering firms we work with. We have quite a focused and a unique approach, only focusing on processes. And our core business is computational fluid dynamics. So very realistic 3D simulation of processes, multi-phase integration of kinetics in CFD to design for the water industry, but also we work a lot on kinetics, and kinetics is really the topic of today. Our company has grown quite significantly. It keeps growing continuously. We have finished around over 100 projects, in fact. But the thing we are actually most proud of is our customer ratings, because if you are a simulation company, you have no choice than offering practical solutions to your customers. And this is where we really are very proud of that. We kind of succeed in that. Okay, let's go to the webinar. These are the presenters of today. So I am Wim Oudenaert. Actually, I did my PhD on the topic of ozonation, of advanced oxidation. And I'm CEO and co-founder of AMT. Then we have Dr. Giacomo Bellandi. He's senior simulation expert at AMT. He did his PhD only on process simulation in the water industry. So there is Giacomo. He's now in the screen. And then we have Celia de Wilde. She's our business development manager. So she's working with a lot of customers as well. So Celia will be looking at the questions you will be asking. So we really invite you to ask a lot of questions. Okay, so let's start with the topic. Before you actually, we dive into the core of the simulation tool and the model, well, we will start talking about some fundamentals that are really essential for you to understand, in order to understand also the content we will be presenting. So let's start with 3 fundamental ozone facts. The first fundamental ozonation fact is ozone decay knows 2 phases. So if you just have a very simple lab experiment, you have an ozone stock solution, and you add some ozone solution to a beaker with natural or real effluent, natural water, effluent, well, typically you see things happening. What typically happens is you add your ozone, this is your starting concentration or the added ozone dose. It typically has a very fast demand. So this is what we call the instantaneous ozone demand or the rapid ozone consumption or demand. But in fact, it's not so instantaneous, it's in milliseconds. And then you have a very slow decay of ozone. If you go to a higher organically loaded water, for example, wastewater effluent, you exactly see the same. Patterns, but now typically the instantaneous or the fast reactions are much faster. But in fact, it's the same principle that happens here. But of course, if you don't add a lot of ozone, it might appear that you never have a residual in wastewater. But typically, that's the key point here. Ozone knows 2 phases. So indeed, ozonation inherently is an advanced oxidation process, because during the decay of ozone, during the fast decomposition, but also during the second slower phase, you have the production of hydroxyl radicals. Quite significantly in natural water, even more significant in wastewater effluent. And then the second fact, so we have these 2 phases. The second fact is target pollutants are removed by both ozone and hydroxyl radicals. So if you have ozone and you want to remove target pollutants, this is what you actually want to do. So you want to use actually a very powerful oxidation mechanism to destroy your organic molecules. It can also be bacteria, it can be viruses, it can be target unwanted pollutants or organisms. So it means if you want to predict the removal of such pollutants or unwanted organisms, you need to also be able to predict both hydroxyl radicals and ozone. If we look just at 5 potential target pollutants, you can see that the reaction rate, which is actually the left axis, the reaction rate with the hydroxyl radicals is quite high for any components. This is because hydroxyl radicals are very reactive and very effective at removing almost any pollutant. Well, let's look at the decay constants of ozone. Well, then you can see we have different categories coming. For example, diclofenac, carbamazepine, they are very susceptible to ozone attack, and they will be removed very easily with ozone. On the contrary, you have 1,4-dioxane. 1,4-dioxane, if you observe a removal, there must be hydroxyl radicals because it can almost not be removed with ozone. The rate constant is way too low. So this is the key message of fact 2. You have different rate constants. So let's look at these two extremes. How does it then impact the system behavior? Well, you have diclofenac and 1,4-dioxane. When we have a very simple banded pipe, so this is just a pipe, this is a CFD simulation. It includes the kinetics. So the kinetics just predict the ozone decay, production of radicals, the oxidation of your micropollutants. You can see if you add it at the top, the diclofenac at the left is almost completely removed in the first seconds or milliseconds of your dosage. So it doesn't even enter or exit this pipe. While if you have a very slow reacting component, 1,4-dioxane, for example, it can really go through the whole facility, and it might escape in the effluent with 70% still left, or 40%, maybe 90% left, but it's very hard to completely remove it. So this is just the impact of the kinetics. You immediately see, if you look at the color scales, red is 100%, dark blue is completely removed, that the kinetic impact is very significant. It's the fact for every component you want to remove. Of course, these are two extremes, but this is a very important fact to remember. And then we have a last fact that is very important. Bromate, which is often of concern, often in drinking water, but of course also in water reuse schemes. Sometimes also when you remove micropollutants from effluent. If, for example, there is a drinking water treatment plant downstream the river, well, bromate is formed by both ozone and hydroxyl radicals. If you look at the left, you see bromide, the ion, and ultimately it forms bromate via a very complex mechanism. So probably I don't have to explain too much details here, but what you have to remember here, look at the orange frame and then the red frame, let's say, you have two pathways. Bromide is either oxidized by ozone or hydroxyl radicals, and both contribute to the formation of bromate. So that's fact number 3. So before we go further, we will go to my colleague, Giacomo Bellandi in Italy. So I'm actually zooming from Belgium, and now we give the floor to Italy. So Giacomo, I will stop sharing and you will be taking over.
Yes, welcome to Italy. So I'm going to share the first basic example that we are going to see today. This is a simple example of a batch reactor. Okay, what you see here is the Sumo platform. The Sumo platform is a graphical user interface which allowed us to host our model there. It's a graphical user interface, so it allows the user to change concentrations, rates, and this kind of things to and allows to run the model and visualize data. So in here you can build your installation, your virtual installation, and in this case it's represented by a single reactor, like a beaker in a lab. And here below we are visualizing both measured and model data. Measured data will be this kind of dots here, which we already included. These are real measurements data from a laboratory test, in which we modeled and which we fit with our ozone profile, predicted ozone. Now, as you can see here, we passed nicely through the measured data, and we observe the typical profile that Wim just explained. So a first drastic drop at the beginning which is the fast consumption of ozone, and then a slow decay in time. So this is linked to the consumption of UV, of the organics contained in the water matrix, and for which we also have an end concentration here, which we are catching, and also the inorganic part. So all this reaction leads to the decay of ozone, but also to the production of radicals, for which in batch experiment, we know that they are really concentrated when you have one spike of ozone, the production of radicals is really concentrated at the beginning. So it really looks like this. So you have a very high production right in the moment where ozone has the most decay occurring. And this is how it looks like. And then it decreases in time as it reacts with the inorganic and organic part of the water, of the substrate. Now, if you know your ozone residual and your hydroxyl radical concentration, then you can also know how much micropollutants are present there, because their reactions rate are known, and you can nicely measure effluent, and concentrations of this experiment. But nonetheless, ultimately, you can include in this complex picture of reaction also the reactions due to bromate formation. So bromate profile, it's also plotted here as a result of the bromide and all other bromate-related compounds that react in presence of ozone and radicals, and the whole net of complex matrix reactions. And here results in an end concentration slightly increasing in this phase, and having a very steep increase in this in the very initial phase. Why? Because this is again the moment in which most of the radicals are present. But we'll see more about this in the next demo. And now I'll give back the word to Wim for the next step of the presentation.
Thanks for the demo, Giacomo. That was a good warm-up. I will go to the presentation again. This one, yeah. So let me see. I should pick the right slides. Yeah, okay, we had the batch demonstration. So in the meantime, I will ask Celia if there are any urgent questions.
Yeah, there were a few questions. One of them is how you can measure HO radicals, okay. And if it's possible to also include other parameters like pH, hardness, temperature, and everything.
Yeah. So the second part of the question about the physical chemical, let's say the chemical characteristics of the wastewater or the water matrix, we will come back to that very extensively. The first part I can very shortly answer. We use it, we use indirect methodologies, of course, by tracking a certain micropollutant, for example, 1,4-dioxane or ibuprofen, or like very resistant chemicals. We can actually indirectly assess the hydroxyl radical exposure. And from the exposure, we go back to the concentration. Yeah. So this batch demonstration was, the goal of this demonstration was to show we will gradually build up the complexity here to not lose you. But Giacomo just showed a very simple batch reactor. And the conclusion from that is, if you add ozone to a beaker, to a batch reactor, reactions are very fast. They happen in a few milliseconds to seconds. And actually most of the bromate formation or radical production or the removal of some pollutants happens very fast. Yeah. So that's what we have shown with the batch demonstration. Of course, we will not stick to batch. You are all interested in larger facilities. So we will definitely go there. So the conclusions from these three facts are, in order to have a valuable simulation model, like a tool you can really use for plant or process or equipment engineering, you need to consider these three facts. First, ozone decay in real water. Second, the removal of target pollutants based on ozone and hydroxyl radicals. And third, if you want to predict bromate formation accurately, you also have to be able to have equations for the production of bromate out of radicals and ozone. So these are three important facts we started with. These are fundamental things that we, from the start, integrated in this model, because otherwise it would really not make a lot of practical sense. So for people not really familiar with process simulation, the interface Giacomo has shown is Sumo. So that is a simulation platform. It's actually a user interface with some mathematical solvers at the back, and they actually solve equations for you and visualize the output. That's what you have seen there. But why would we do this, and what is really a process simulation model? It's just one slide to give you some more background. As a process technologist or a designer or an engineer or an operator, you want to actually have a desired system. What your desired system is depends a bit on your objectives. It can be minimal bromate formation. It can be maximum target pollutant removal, maybe one specific target pollutant. Maybe you want to lower the capital investments by a reduction of your reactor size. Maybe you want to reduce your OPEX. Your desired system depends from case to case, but you want to go there. And typically, this is what we also announced in this video when we announced the webinar. A lot of experimenting has to be done. You have to measure, you have to do some piloting on site, and it's not a very easy process. It knows ups and downs, and you have safety factors to consider on site with piloting, and measuring bromate micropollutants. It's not all that easy. So what you can do is actually you build a system, a simulation model of your system, and you can use that model if it's very realistic to run virtual experiments. This is called simulations. And you actually end up with your virtual desired system. Imagine you want to reduce bromate, you use the model, you run different chemical dosing strategies, you test and compare different ozone dosing strategies with each other. Imagine you have found the best scenario for your specific matrix. Well, you can actually go back to reality and build that system, or at least start piloting that system. That's a bit the concept and the shortcut, or the very effective and elegant way we want to offer here with a very realistic model. What is a very realistic model? What is an engineering model? It needs two inputs. One is water matrix data, because I shouldn't explain to you as water professionals, as ozonation professionals, that every water matrix is different and that your system performance depends on that. It means DOC, the COD, so the organics, the soft organic carbon, chemical oxygen demand, UV spectrum, conductivity, target pollutants, bromide, carbonates, etc., etc. pH is also part of that. These are water matrix data you can measure. On the other hand, you have process settings, which ozone dose, which chemical dose, maybe you want to add some peroxide or so, volume and flow rates, volumes of your compartments, things like that. So they should not be built yet. You can actually envision them and put them in the model. You feed that to the process model. These are the two main inputs. I don't think everybody has a good idea about these two inputs typically. What the process model consists of is a set of mathematical process equations. I promise you one thing, these are the only equations we will be showing. We will be focusing on the application side, but just to give you an understanding, the process consists of mass balances. And the mass balance is nothing else than the dC over dt. For example, the change of 1,4-dioxane concentration as function of time. And you can see that there is a minus after 1,4-dioxane because it's being consumed or removed. There is a plus sign after the equation of bromate, which means it is being formed. That is the core of a process model. Of course, it's quite sophisticated because it includes all these reactions, carbonates, bromides, target pollutants, and things like that. But in the end, if you have this set up for your matrix, then you can actually start predicting ozone decay, target pollutant removal, bromate, and disinfection in your specific plants, depending on your specific process settings which you can actually play with the model. So that is the real core concept of using a simulation model as an engineering tool. I think if you're a practitioner, you can kind of grasp the value, because imagine the model works fine. It might give you a very good high resolution data. And you can actually run much more, actually an unlimited amount of experiments. We show just some prediction examples, from different sources. One is a surface water from the Netherlands, from Dunea, which is a drinking water treatment plant treating surface water. And then we have secondary effluent from the United States, from Virginia, HRSD, the utility there, and their innovative Swift water reuse, indirect potable reuse project. So very different matrices, very different bromide concentrations, for example. Let's look at how we predicted bromate and also target contaminants. What you immediately see if you look at the left side, the bromate being formed in both matrices is very different. Yeah. So you are talking about the micrograms per liter range, or you are talking about tens of micrograms per liter. I should add here that the bottom case is with very high bromide in the influent and with no bromate suppression. Yeah, of course, these people are suppressing it smartly, so the levels actually can be much lower. Huh? But I'm just demonstrating you that we can predict bromate as function of operational settings. For example, the ozone dose or the UV or the peroxide versus ozone ratio. So the blue bars all are the predictions. The green bars are the data, the measured data. So you can see that you can run a lot of scenarios and then compare it with data. But of course, once this is set up, you can run much more scenarios and don't have to measure all the time. On the right-hand side, what you can also see is that the amount of micropollutants or target pollutants we can include in the model is unlimited. So it is quite unlimited. Even if you can only measure one, you can still predict like 50 or 20 or 10. That's not really a problem. And you clearly see the differences in rates, right? In the removal. For dioxane, you also see the same. Of course, it goes down if the ozone dose goes up. And you can end up with a 50% removal, of course, in an organic matrix of like effluent. So this is the prediction of the AMOZONE model. So this is our new simulation tool, we have called it. Now we go to practice. So these were some fundamental understandings for you to grasp the concept. Of course, what is very important to ask ourselves is, okay, imagine you have such a tool. What would be the practical value from a process engineering perspective? We will be showing this using demos. So we will be going back to Italy within a while, but let me first explain a bit. So you can actually do 4 things with such a model, 4 main categories. Of course, first, it allows you to have a very in-depth process understanding. What I mean with this is, for example, what is the amount of bromate being formed in your side stream? How does the ozone decay vary throughout my whole plant as function of water matrix changes? Where should I locate my sensor? What is the decay of different target pollutants throughout the train? Where is the specific removal of each of the components throughout the train? This is what I mean with process understanding. But of course, if we come to practice, understanding a process is not enough. You want to, for example, select the technology. Is ozone a very good technology for this water? Or you want to design your process once you have selected your ozonation technology. And once you have built your plant, you want to operate it. So these are 3 very important categories. Let's start with the first one, technology selection. So the questions we can ask ourselves here is, how suitable would be ozone here for this specific matrix? If it would be suitable, we mean what would be the bromate formation potential? Can we suppress bromate in this matrix? What would be, given the matrix and the dose we would like to apply, what would be the removal of the target pollutants? Can we increase or reduce increase the value of real life piloting, or can we reduce the effort? Can we maybe take a few samples and complement the data with the model, high resolution data? and things like that. So these are very important questions when one talks about technology selection. So Giacomo will now be demonstrating this in a demo in Sumo. So Giacomo, I will be giving the floor to you again.
Maybe if I can jump in with some questions, because we received quite a lot. Maybe the first one, what data sets do you need from batch tests to simulate an upscale to full scale? So maybe if you can give some information about that. And then also, what is the difference for your modeling if you deliver semi-batch test data? So continuously adding ozone into the reactor instead of batch test, adding saturated ozone water to sample. So maybe if you can answer that before we switch back to a demo. And I saw there was another question Giacomo will answer as well about stoichiometric and kinetic model.
Okay. Yeah, well, I can take this one. Giacomo, you can complement me, and also go further when you have the demos. Well, first, when we started building this model a few years ago, the first question we asked ourselves was, can we use as much as easy to measure variables to feed the model with if we run it? Second, can we also select as much as we can real-time variables? So what is very important is basic variables here. We are talking about conductivity. We are talking about the carbonates concentration, the pH, UV spectrum, UV 254, for example, COD, DOC, and of course the bromide. If you have an idea of the bromide fluctuation of the range and your target pollutants. I have almost covered. I've covered most of the aspects. Am I correct, Giacomo?
Yeah, sure. Indeed, that's perfectly true. Yeah.
Back to the second question on the semi-batch. Well, indeed, we have gas transfer and semi-batch in our model. Giacomo has shown the first batch, which was a liquid system, but you can actually go deeper on that now, Giacomo, I suppose.
Yes, we'll go step by step, deeper and deeper. Actually, most of these questions are going to be answered also about the stoichiometric coefficients. These are going to be answered in the next demos. What I can anticipate is that the stoichiometry of the model doesn't change, remains the same. The coefficient regarding the strictly linked to the type of water matrix might be adjusted for a completely different water, but we'll show an example of a calibrated example on one plant and a validation actually on a completely different plant afterwards. So just to tease you a bit, but let's go gradually and let's build up pressure little by little. So in my screen now, you can see a slightly more improved, like a continuous plant here, in which you have some surface water entering a reactor, a single reactor in which we are inflating our ozone gas. Now, the surface water, let's assume it's initially as a constant composition, and then it starts changing because of some surface water. So weather is changing and its composition changes. So the concentration of the compounds is going to rise slightly. Here we see alkalinity is going to increase. We see like the bromide, nitrite, and ammonia are going to increase, and the UVA, so the organics in the water, are going to increase as well. And pH is also going to change. So how this is going to translate in what effects does it has to on our reactor, on our results, so on our treatment. So again, we are blowing a constant flow of ozone gas here in the reactor, and this is actually the profile that we obtain in the 4 days of simulation before we have a certain a constant influent with a less concentrated water coming in, still surface water, and then little by little the more concentrated water kicks in, and it's visible because ozone gets more depleted by the organics and also by the inorganic carbon in the water, which is also interacting with radicals here. You see, initially we have more radicals, and then they are depleted by the water matrix a little bit. So how does this translate in the effluent organics, in the effluent UVA? So we have a little increase due to the capacity of the oxidation process. So we have a slight increase in the effluent from our reactor. And what happens to bromide? So interestingly, even though bromide is increasing, our bromide is not. So it's decreasing with the more concentrated water coming in. Why? The reason for this is because the organics reacting with ozone are more, we have more organics in the second part of the graph, which consume more ozone, a more complex matrix of water, which is scavenging more radicals. So there is less chance of forming bromide in this second part, although bromide is in excess. So, and as we've seen before, just an example of what is happening to a couple of micropollutants. We'll see more of them. We've been including nearly 20 micropollutants in there, which most of them we know the rate constants with ozone and radicals, but some we had to derive it. But I'm just showing some of them here, and we see, for instance, atrazine, which is most sensitive to radicals rather than ozone, not really sensitive to ozone. So, and it senses this drops in radicals due to the more concentrated water matrix in the second part of the run, and as well also bentazone. So it's also showing an increase in time due to the less availability of ozone to oxidize it. So this is the complete picture. I hope it's a bit more clear. And now we're going back to the presentation of Ben.
Okay, we're back. Thanks, Giacomo, for this demonstration. So this was the technology selection side. So we have up to now seen batch. We have seen this very simple flow-through reactor, semi-batch actually. That can be a lab semi-batch reactor, for example, or continuous flow system. But now the interesting part comes, of course, if we look at process design. And now we really go to the engineering side. So the questions we have here are, for example, what will be the ozone residual throughout the train, including the side stream? Where do we have, for example, to put some sensors if you want to, I don't know, you want to monitor your ozone concentration, for example. How far does the ozone reach as function of your characteristics? What is the optimal sizing in view of current and future water characteristics? We have seen a couple of customers that plan in the future to start blending, for example, different surface waters. Well, what will be the impact on your ozone system if it were designed, for example, only for your one surface water, or your effluent will change, things like that. Selection of injection technology, both have pros and cons, fine bubble diffusion, side stream injection. What's actually happening? How is bromide being formed in both systems as function as length of the column in your side stream system? And we have also seen customers that, for example, want to implement ozonation at a certain specific plant. Let's call it plant A. They have done 2 years of piloting work, and then they consider putting it at plant B as well, maybe 100 kilometers or miles away. Well, the question you can ask yourself also is then, can you then also do the same, repeat the same with the virtual piloting methodology with the model and have such assessments? Or if you would go on site and start testing, can you actually get more out of this or reduce the effort? So that is all process design related. So before we go to Giacomo, I will ask Celia if there is an urgent question to be answered.
Yeah, thank you, Wim. Actually, there are two questions we will pass to you for now. One of them is what time step you need to run fast reactions, like involving the radicals. Has any sensitivity testing been done to see the impact from the time step? So that's one question. And then the other is how the model deals with a mixture of, for example, 50 micropollutants, of which only for 30 the ozone rate constant is known, but we don't know for the other 20. So maybe you can answer those two questions before we continue.
So Giacomo, maybe that's a good, those are two questions for you, right?
Yeah, sure, I can take that on. So for the sensitivity analysis, yes, we're doing that. It's a very extensive model. So we are on the testing of it as well. We did most of the sensitivity analysis with a couple of new exciting examples from new clients. And yeah, well, we can also talk about more in detail in a separate session. But it's very interesting. That's all I can say right now for time restrictions, I'm afraid. But and for what concerns the micropollutants. Yeah, so we can include, as Wim said, we can include as many as we want. Of course, the limitation is how much of these micropollutants do we know. The reaction rates are known. If the reaction rates are known, they can be included easily in the model. We have, at the moment, about 20 micropollutants already implemented there. And more can follow. What is interesting to know and to keep in mind is that once you know one of these or a couple of these micropollutants, they're acting like probe components, and they will tell you lots of information about all the others. So in terms of the ones that we don't know the kinetics, then it becomes more tricky and might require some experimental, separate experiment, lab experiments to derive some more information. But that's absolutely possible.
Yeah, Giacomo, I think related to that, what is interesting is that we have discovered for some of the micropollutants that the rates constants published in literature, so for some of them, they are quite uncertain. We immediately see this in the model, that they don't make sense.
Absolutely. Actually, one time I filled in the wrong kinetic for one of and the model told me, hey, you're completely off. It was a typo. But actually, yeah, it's true. So what is also in literature is it's quite varying, and the information you get from the model, it's really impressive. Yeah. Okay, so I will share again my screen, and we'll go to a bit more detailed demo. So what you see here is it's a full-scale installation with a clarified effluent that it's incoming the treatment train. It's going through, it's split, equivalently split here, and it's going through a side stream injection in which we can dose some ozone directly in a small volume, and then it's joining the mainstream, and then the reaction is led along the train. Or the same installation can be used switching off the side stream and comparing with and using it as a bubble column installation. So blowing ozone gas through the bubble column. It's a counter current in this case. We also have a co-current in case it's more interesting. But I think in this case we have a counter current in which we blow some ozone gas from the bottom to the top, and the liquid it's going obviously in the other direction. And then the rest of the reaction happens in the rest of the train and the rest of the columns. So what you see here below, it's like sample points along the whole treatment train. So you have the side stream injection, the SL6 tank, and then you have the first bubble column represented by 5 locations, 1, 2, 3, 4, and 5. So water is going through the train in this direction, while in this case, ozone gas, it's inflated at the bottom of column 1, so this point, and it's flowing upstream. So it's going in this direction. So what you see here is the classical profile of a countercurrent bubble column, which you are blowing ozone gas here. You're dissolving most of the ozone in the first section, so close to the bottom, obviously. And some of the reaction happens in the upper sections here. Some of the ozone flows through the rest of the treatment train, and we can see it remaining here. So we can highlight the ozone profile through the treatment train. So the consumption of ozone can be like synthesized in the consumption, in this case, of UVA, but more reactions are consuming ozone in the model, like also the reaction with the nitrogen compounds, with the inorganic carbons, and then etc., etc. So here we see that in the first section, at the bottom of the column, we have most of the depletion of the organics, and at the same time, the production of radicals. So in this exact position, we know how much radicals are produced by each of the main reactions responsible for this, and also what is scavenging mainly the radicals, and what is along the train the concentration of our micropollutants. Here are an example of about 10 of them. So how does it look like if instead of a bubble column in which we generate in the end about 10 micrograms per liter of bromate, how does it look like if we switch off the bubble column and we switch on the side stream injection? So what is going to happen is that the ozone here obviously is going to decrease and to disappear, and what we are doing is that we are inflating ozone right at the side stream here, generating a lot of bromate already in the first small section here, so producing all the radicals at the beginning of the train. Also the scavenging is going to be more important there, and the concentration of the micropollutant is going to decrease, mostly at the beginning, where we are dosing the ozonated the ozone gas in this small tank for the side stream injection. So now, as compared to before, we are producing much more ozone as it's normally occurring, as comparing side stream with bubble column. So let's assume we want to knock down this bromate. We want to knock down this bromate, and we, for instance, dose 5 milligrams per liter of peroxide in the influent. So what is peroxide doing is scavenging part of the radicals and having also other interactions with ozone and the water matrix. But the main message is that peroxide is scavenging radicals, and it's scavenging much more radicals that normally occur, and preventing the formation of bromine. So we are going from 13 micrograms per liter back to 8, 7, 8. All right. So another solution that it's possible to implement to knock down the formation of bromate is to dose hypochlorous acid. Hypochlorous acid reacts with ammonia, if any, in the influent, but here we have a clarified effluent, so there is normally a small remaining part of the ammonia, and forms monochloramine, which is also a radical scavenging. But what is also doing hypochlorous acid, being a strong acid, it's also reacting with organics, the organics fraction, and in this case it helps, in that sense, helps ozone in removing the UVA fraction. So this allows to have a longer part, a longer tail of ozone through the reactor, and actually it helps also removing a larger part of the compounds that are more sensitive to ozone. In this case, also atrazine, because in this case atrazine it's decreasing because we have more radicals available as compared to the dosage of peroxide. So you see all these complex reactions that are taking place, and it's very interesting to observe, at least for me, I hope also for you. So another interesting thing to observe is also what if the content of nitrite, for instance, of this water will drop to a very low value. So this is going to affect the reaction with ozone. And what we observe here, it's a slight increase of bromate. Why? Because this is due to the slightly higher availability of ozone for reacting with in the net of the reactions of bromate. So, but what is also very, very important in this net of reactions is the alkalinity. So that the inorganic part of the carbon, which has a very strong impact on radicals, and therefore also on bromate formation. So with the same profile of ozone, slightly same, fairly the same, we have a larger production of bromate only due to alkalinity. So with this, we can go back to the rest of the presentation, and I'm going to prepare the last demo.
Okay, so I guess there must be questions. So Celia, will go shortly back to you. Maybe one question.
Yes, indeed.
Yeah.
There are a lot of questions later, but
we have a few questions, but I think a question for now would be if you have any thoughts of integrating the sumo-based ozone process model with CFD modeling.
Mm-hmm. Well, the graphs you have shown, you have seen with this simple pipe at the beginning, where we were comparing diclofenac, one for dioxane, there was direct coupling of the kinetic model with the CFD model. Yeah. So that's definitely possible.
Yes.
And that's a different, people often confuse such modeling with CFD. Yeah? They have different purposes. For example, CFD will tell you, how should we design a nozzle? Or what is the impact of putting a baffle here or there? This model will give you sizing information, conversion information. It allows you to simulate 200 days. So that's a different application. Perfectly possible. I think it's a very good question. Let's go to the operation. So because you have selection, imagine we go for ozone, okay, let's build the plant. You will design your plant. Okay, when you have designed your plant, you have to operate it. Of course, you already see it coming. We aimed at real-time sensors. So we will next year also make this a real digital twin. It's called a digital twin. So it's a copy of the real plant that can actually run in parallel with the real plant. But of course, if it's only a model, you cannot do too many things wrong. And you can actually in real time experiment with it, with the plant. Or if it predicts your bromate and real-time micropollutants, it is, of course, of very good information. If you look at regulatory compliance operations, smart operations based on the matrix and things like that. So smart dosing, the testing of different control strategies, because Sumo allows, this platform allows to integrate controllers. We have not go in there because we want to keep the complexity limited, but you can control the plant also in this virtual platform, so you can experiment with control strategies. So let's go back to Giacomo now, and he will be showing a dynamic simulation, which means that the model is being fed with real plant data of a very long period of time.
Yes, thanks, Wim. So what you see now is a simulation running it's going to run for 270 days. So simulation days, and should take about 6 minutes. This is a dynamic influent of a surface water entering an actual installation, an existing installation in Europe. So, and the installation has a side stream injection, as we have seen before, in which a fixed dose of ozone it's given, and then it's going to react in the main reactor. So it's worth mentioning so that we have for this installation we have influent data on influent UVA and effluent UVA. So we have very limited data, but nonetheless we can we are complementing the available data with other information that we have on surface water. So this is part of the job to fill the gaps on the data. So because in real life data are not always available, not always perfect and clean, and sometimes only a part of the data are available. So in this case, we are running a simulation of 270 days with a very limited data set, only UVA. So in this case, we observe the UVA absorbance, the bromate formed online, so it's all predicted data, and the ozone resulting, so the residual ozone in the reactor here. So what is also good to mention is that the model for this installation has not been calibrated. We're using the parameters that we calibrated on a different plant, actually the plant we have seen before, which is in the US, which is treating clarified effluent from a wastewater treatment plant. And we applied it here just to, as a first trial. And we are applying it to a completely different plant, treating actually a different water, maybe with a similar matrix, but it's a surface water, whereas before it was clarified effluent. So what we can observe apart from the rest is also other information that we don't normally have. So the profile of the micropollutants, of some of the micropollutants in time. So what is going to happen to these guys? Meanwhile, the water is the composition is changing. How is it changing the conversion of our micropollutants? And also the conversion in time, how is it going to look? We are looking at isopromide conversion, and here we see that at day 84, we have a drop in conversion. Probably it's due to the different composition of the organics coming in. Now we can check the effluent for all kinds of different compounds included in the model. Also, pH and carbonate equilibriums are possible to observe. But let me go to the end of the story. What we are seeing here is the end concentration of UVA. The green is simulated data. You see it progressing little by little. We are now at day 120 almost. And we are going through the measured data points, which are online data online data. It's from an online sensor. So slowly, but not too slowly, we are getting through the entire data set, and also getting more information about the potentially resulting bromate. Unfortunately, we don't have information about the effluent bromate in this case, but we can have rather robust idea of what is going to happen to our micropollutants and their conversion in time.
So Giacomo, I will interrupt you.
Yes, please.
Fine, we are losing a bit the time. We have to go to the conclusions.
Yes.
But I think people have put this in their agendas. The end of the meeting, so we have to really go to the conclusion. We can go back to this for the people that have time left within like 5 minutes or so. Is it fine?
Yes, yes, please.
So I will share my screen again. We will go to the conclusions. So, well, let's go back to the other slides to give you a bit of an overview what we have covered so far. We have focused on process understanding. This was more the fundamentals, technology selection, process design, comparing different technologies, injection, sizings, flow rates. And then we go to the operation. And the example Giacomo was now showing was actually a process operation. And you can see in a few minutes, yeah, we really have simulated an extensive data set of 220 days. So that is, of course, another benefit of simulation, that it can go very fast compared to the real time. What are the conclusions? So this brings it all a bit together, this slide. This slide summarizes the most important aspects that actually impact ozonation process performance and cost. In the end, it's these two things that matter. It's performance, because you want to reach a certain goal, but also you don't pay any amount for that. It's both operational and capital investment that are very important. These four categories are, of course, driving this. First, you have the water matrix properties. We are talking about all these variables we have shown. Second, we are talking about equipment and system design. How do you design your injection systems? How do you size your reactors? How many nozzles? Type and geometry. I mean, the positioning of your equipment. It has a huge impact, of course, also on the performance and the cost. And it might vary across water matrices. And then you have the process parameters, which is Are you going to dose any chemicals? If you are going to dose chemicals, which ones? What will be the impact on the conversions? Because there's always a trade-off, right? So you go to bromate suppression, but you also lose some of your target pollutant removal, things like that, gas flow rates, feed gas. And of course, when you operate a plant, you also have human factors, but such a model could also help in, for example, getting operators familiar with the plant. If they are, for example, wastewater operators, they have to get familiar with an ozonation plant to operate. So these are really 4 categories that are really summarizing the core of what we have tried to be covering. And most importantly, I think, is that the model really covers these three other important non-human aspects. What is the current status? Well, the model is currently being applied at several plants in Europe and the US. Wastewater effluent, drinking water ozonation, different purposes, different objectives, very different water matrices. The services and the support of using this model, applying it to assist piloting, to conduct virtual piloting before real trials, it is currently already available through AM Team. So if you have a case, just email info@amteam.com. We will be more than glad to support it, or reply the emails after this webinar. You can find us. But also the simulation tool will become available soon, because if you are a plant designer and you have to really do this a lot, we can imagine that this has some value for you. Huh? Our goal was with this tool to remove significant practical, regulatory, and financial barriers standing in the way to successful application of ozonation. We really hope to support this with this. Your feedback will be extremely welcome, so please share your feedback. We will continue after this with a couple of other questions, but just imagine you would be leaving. I also want to acknowledge our partners, our very good partner, Dynamita from France. So they are actually the software builder of this very good tool, Sumo. Sumo is very successful in the wastewater business to simulate in a very accessible and easy way wastewater treatment plants, but it also has very good physical chemical properties, and that's why we really use Sumo in this case. HRSD, this is a utility in the US. From day one, they really worked with us on this, and it has been a great partner. Without them, it would have been impossible to develop this model. And then we have Dunea, which is a plant in the Netherlands, a utility, a drinking water utility, which was also very supportive in this trajectory. So AMOZONE, as we call our model, AMOZONE is actually an official product of AM Team right now. Another announcement, within 2 days, there is another webinar of the International Ozone Association, specifically on CFD. And we will also be contributing to that. But if you're interested, go to that web link, or just Google IOA Ozone CFD webinar, and you will also hit the page. Yeah, very interesting webinar with very good speakers, especially from the US, but we have a European contribution in that. So we will continue after that for the people that have to leave now or are leaving. While we would really hope to connect with you, we would hope to interact, get your questions, get your feedback. And if you want to have a meeting with us to see where we can collaborate, please send us an email and reach out. But we really want to thank you for your engagement, the good questions. And I really invite you to also follow us, especially on LinkedIn. We are very active and really share the latest updates. But on our website, there are a lot of blog posts as well. Yeah. So we will close here for the people that want to leave. For the people that want to have additional questions answered, well, we will go back to Celia.
Thank you, Wim. There are still some questions left. One of them is if we include process variables like cooling water temperature, mass transfer efficiency, DO concentration, and then also how we handle total suspended solids concentration and if it affects the results. Mm-hmm. So maybe first we can answer these questions, and then we...
Yeah, regarding temperature, it is included for some of the reaction constants and adjustment for temperature. That it's included, and we're extending it to all of them. that it's so that we have a complete picture of the interaction of ozone with temperature. Yes. Yeah.
Dissolved oxygen, for example, indeed, it can be relevant if you have a downstream biofilter, for example, or other downstream processes. Yeah, it's an easy one, right, Giacomo? I don't think it's included right now, DO.
No, it's not included, but actually it is a component that we have, so we can easily include it in the...
Exactly. And regarding the other ones, for example, bubble sizes, that can be altered, that is no problem.
Yeah. It's completely customizable. Bubble size and yeah, gas holdup can be customized. KLA. These are all features of the aeration model implemented by Insumo. Yeah.
Another important one, I think, for the people that are still here is we haven't talked about operational costs. Real-time calculation of operational costs as function of generator capacity, or if you design liquid oxygen on-site production of pure oxygen. These things are future features. We will be including them as well in the planned design. Yeah, but that's just a side remark. I was just thinking about this when I heard this question. I don't know if there are additional ones.
Yeah, maybe well, there were a few questions concerning the water matrix. I think yeah, you guys can tell there are different water sources: surface water, drinking water, and then here there was also a question if, for example, seawater can also be put into the model.
Yeah, I would say I'm now showing like the model finished, the run finished, so we can see the actual the result of a changing water matrix, because this is something changing. We have seen it before, so this is like going through the UVA measurements. We have seen it before, the change in the water composition with changing nitrogen components, alkalinity, so inorganic carbon, dissolved organic carbon changes. So, these are all things that are taken into account. And so more extreme water matrices can be included. At the moment, I wouldn't say we have a specific limitation on that. Yeah.
Yeah. Indeed, seawater, we have not modeled that so far, seawater.
No.
Of course, it will impact certain things. It will impact your gas transfer. You will have to, of course, account for that. We can, in the model, we have to like tune the model if the matrix is very different, but also it will affect the kinetics. It's a matter of, yeah, making the model ready for that specific water. But I think in terms of, yeah, scavenging might be a bit higher, salinity. It's a matter of, yeah, calibrating the model for that specific seawater. Then that's quite different. Yeah, quite different matrix. So we expect some differences in the parameters.
Yeah, in that case. Yes.
With regard to the scavenging, especially, and the ozone consumption, decay rates of ozone. Yeah.
Yes.
Yeah, but these are things also. If you look at the future usage of the model, ideally, of course, if you ask us, what data do you need to have a good model for our system? We can, of course, provide you with a very good list. Typically, it's a good batch experiment and some measurements, basic characteristics. We can, of course, suggest this wish list. But we have plans where these things are not available, or they have historic data. Well, based on, we have shown this in the past, right, Giacomo, that we start calibrating the model based on what we have, and it brings us a long way already.
Yes.
That's a good thing about
lots of information. Yeah.
Okay.
Yeah.
Maybe can I jump back in with some questions? There's another one concerning the optimal side stream size. If you can play with the side stream flow versus the main flow, and then also if we are present in the aquaculture industry. So those are two remaining questions, and then a practical one if today's presentation will be available.
Mm-hmm.
So I'll let you maybe start with the side stream versus main flow question.
Yeah, that is totally possible. Yeah, we have implemented an additional example of PID controller based on effluent bromate. That's possible, and that's as well possible to simulate the splitting, how much we are splitting between the side stream and the mainstream. That's perfectly possible. Yeah.
Indeed, and then the matrix becomes very important because the amount of bromate you will form or the amount of removal of a certain pollutant you might already have in the side stream is extremely matrix dependent. Probably we have a lot of practitioners here. This is also not surprising, but these things can be assessed. Regarding the presentation, we will not make it available to the wide public right now. But I will add a big addition. If you have specific questions or you want specific information, we can always look what we can do, and you just have to contact us. We are quite open in sharing, and so feel free to contact us, and we can see if we can answer your needs.
And then the question about the aquaculture industry, maybe.
Oh yeah, aquaculture indeed. Well, we are actually setting up a couple of projects in the CFD at the CFD site, computational fluid dynamics. It's actually very similar. We call them reactors, while people in the aquaculture industry call it ponds or fish farms. We look at them from a reactor perspective. A fish is consuming oxygen just like activated sludge, but it can be perfectly applicable, because it's very similar engineering. Yeah, you have a matrix, you have a specific chemistry going on, so it's a matter of calibrating the model. Yeah, we expect, of course, that ozone decay will be quite significantly different. Huh? Yeah.
There's another question about the mixing. If we can also use static mixer for the mixing mainstream and oxidants prior to the reaction. I think this is almost into our field of CFD modeling.
Yeah, yeah, that's a CFD question can solve the hydrodynamic part indeed, but there must be ways to also mimic this in this process simulation tool. It's an extremely intensive mixing. Yeah, for example, you can run a very simple CFD simulation. What we as a company often do is, out of a CFD simulation, we derive a very simple hydrodynamic model in such a flow sheet model. We call it flow sheet model, for example, in Sumo. And it's representing the hydrodynamics quite accurately. So that's definitely an option. Yeah. Yeah, we have simulated the Venturi. You did it, Giacomo, a few days back without static mixer. Of course, it's a disaster.
Yeah, it was fun.
Regarding the TSS, we forgot to answer this. TSS will, of course, definitely impact especially the fast ozone consumption part. Yeah. But again, this part is included in the model structure. Huh? So this will, yeah. We will have to see at the plant if there is TSS measurements, for example, if we can look at TSS and the correlation between the ozone decay, such things. Turbidity. Yeah.
I think for the questions, this was it. And also, we went almost 20 minutes past our time, so I think it's a good question and answer session. And like you said, if there are still questions remaining, you can always contact us.
We were very limited in time. It's a very heavy topic. It's so much to present in 1 hour. So that's why we couldn't cover everything. But indeed, we will go through the questions afterwards, and we will try to answer as much as we can. Huh? Yeah. But for everybody that stayed until now, a big thank you, because you are the diehards. It's very intensive. It's more intensive than a physical conference. Following a screen for 1 hour or 1 hour and 20 minutes. So thanks for staying so long.